Hello, in this video, I'm going to show you how to use Midas General to do buckling analysis. Right? So here, such as um, this is Midas General. We create a structure similarly. So we need to open a new project. Done. Okay. Okay. So um, we are in a new project. We create a structure type. Similarly, we want to do two-dimensional analysis as a simplification because since 3D may require a little bit more experience in Maths General. So we do the XY plane firstly. Let's check the unit system. And we want to use inch and kips. So everything is for steel. So we create a structure. We just create some nodes there. So we create a load. So here, if you can see, I would like to create a structure member with 120 inches. So that we need to create two loads, one at the bottom and the other one at the top. So we can create distance. We can have a copy. So we have the 120. We have number of times one. So create how many? Let's see. Okay. Yeah, okay. Let's zoom in over here. Okay. Oh, this is a XY. I can show the XY. Not fitting. And I believe one is the bottom, the other one is on the top. Okay. So that's the one and two. So now we create the element. So we just collect one and two using beam elements so that we can have the one and then the two. Apply. So we create a member over here. So that's the column we're going to use. Properties. We create some properties here. Material, we use steel. A36. And A36, pretty much same as we did before. And we can also add a section for that. So what we use the W section here, W shape, PISC, section name. We could use it W. Let's use a typical column. We use W10. For example, we can use W10 by 112. So you can see the moment of inertial. So the moment of inertial about the no neither axis IYY. That's about 716. 716. So we can input the 716 to the Excel spreadsheet. So we calculate the owner buckling stress is about this number, and that's about 14,000 to 31. So that's the number we got to verify using the software, or we can use this number. This is the theoretical number, and verify our software's input over here. So that's the IYY, I believe. The IZZ will be used as a 3D analysis here. Let's just keep this one. Right. So we have the W10 by 11, 112 over here. So now we can just next step we're going to do is to apply some boundary conditions. Let's save this one. So this is a buckling W shape. Okay, so let's apply boundary conditions. So at the bottom, we use the pin select. Use the pin. Select the bottom. So it's a pin. The top, we have a loader. So zoner, we only restrict the X direction. Right, so loader now. We can show whether we applied it correctly by checking the boundary condition. Yeah, I think that's correct. That's correct. So save it. Then we apply a vertical load. Vertical load. We need to define a static load case. This is the axle load the case. This is the dead load. Add the dead load. We apply a the load on top. So we you can put any number, but I would suggest to use a unit number. So later on we can show that the actual node is equal to the unit node times the eigenvalue vector here. So we apply -1, -1 there. I can show everything here. We want to show that the load values. And show the load value here. The load value is -1. So that's the column we have here. So basically, we know this column will be bent, will be buckled under this force if we increase the load here from 1 to the critical buckling load. But before we do any analysis here, I would say in order to have a buckling analysis, we'd better have more elements here. Because if we have only one element here, the software will not be able to give us very accurate results, such as we can divide this number to 10. So we can go back to node and element here, and we divide this by 10. 10 more. So we just need to select this one. So we have 10 element now. So basically, if we have 10 elements, we could analyze it to have 10 different buckling stresses, buckling shapes here. So we save it and we go to, we have already applied the load. So we go to the analysis, we do buckling analysis. We do buckling analysis here. So number of modes, how many modes we have. Since when you do buckling analysis, the critical buckling node mathematically could be equal to n squared times pi squared times ei over l squared. So n is a integer number ranging from 1, 2, 3, 4, whatever. So depending on the how many n's you want to have here, such as here we can have 5, 5 in here. So we wanted to show that positive values only. We wanted to check only one direction, and we have only x or force on p. Okay, so we can uncheck this now. So we consider axial load. We do the buckling analysis for the compression force here, a scale factor 1. So we just apply the 1 to any other number. So we make it so add this node case for analysis. So that's it. So we do the analysis. And the analysis is done. It's done. So then we can okay. We can check the results such as the model shape. So we wanted to check the model shape 1. That is the model shape 1. That's a model shape 1. You can check model shape 5. So basically we'll have 1, 2, 3, 4, 5, 5 half sine waves. And if you check model shape 3, you would have 1, 2, 3. So that's the model shape. How about the critical buckling node? And that's we can show the table. I click table over here. So we have the eigenvalues here. So the first eigenvalue is 400601. So the eigenvalue times the number one, that would be the critical Berkeley node. Looks like that's not inconsistent with what we have over here. Let's see whether we use the correct uh, I number. Let's see. Probably the load is based on the smaller I value. And let's see whether we can use check the smaller value. Okay, let's use 236 instead. 236. Okay, and looks like the software automatically picks the smaller of these two. And if we go back to uh, the number, so that's 4006. Actually, we should be able to output this to Excel spreadsheet. So this is the output. You can copy those numbers to here. So that's the model shape. That's very, very close, very close. But there are some uh, uh, discrepancy there, but very close. And maybe that's how the pi is calculated. But we can check the second mode, such as this is for mode shape equal to 1. This is a mode 1. This is a mode 1. So the mode 2 would be this number, mode 1's number times 2 times square. And so that's comparable to what we have here, but slightly discrepancy here. But we can increase the accuracy over here, such as we use more element. So we can go back to the element result here, and we can change the results to more elements, such as we use 100 elements, and we divide everything to 10, and we just select everything here. We divide everything to, so we use more element here. Let's say whether we can get a more accurate result, right? So from the analysis, it may take longer because we have a larger model. Okay, so we have 100. So now let's check the result here. So has that increased? No, not increased. Okay, this is the model 3. So you can have more model here. This is the model 1, and model 5. So basically the shape increases here, but the results pretty much the same. And the eigenvalue pretty much the same. Let's double check. So there are some, slightly different. So if we use more element, we use more element here. Okay, looks like still slightly different, but then let's check the mode 3. Mode 3 is equal to the mode 1 times 3 square. That's even larger. But they are in the same. I believe that's some that's the theoretical value with numerical value. So there are still some discrepancy here, but the discrepancy, especially for the first model ship, we know the first model ship will control, right? The discrepancy here is very small. But for the higher model ship, the discrepancy is more significant. But that's not a big concern because the, um, the controlling critical buckling node is the model one, right? That's a model one controlling. Model one controls any time when you apply a force equal to eigenvalue of the force mode, the column buckles. So basically, you could not apply any additional node. And that's the buckling analysis of a column. So actually, I believe the buckling, you could also use buckling analysis to check uh, the, the critical buckling node for any structure instead of a column, such as you may have a tower made of trusses, or you have a frame over here on the compression. You can also check that critical buckling node over there. And I'm going to leave that to you as a probably as a homework. I think that's a video over here. Thank you. Theory. Stop.